All right, welcome back. So we're still on week 3, lesson 3.1, and we're still talking about nature's design principles. And this little video is on the half of life's principles that revolve around adapting and evolving. So maybe it was just a few minutes ago, or maybe earlier this week, we were just looking at life's principles. And it will be really helpful to have a copy of life's principles in either the butterfly form or your list form as we go through the rest of this lecture. So if you don't have it in front of you, why don't you just hit pause real quick and go get it. So in this little video, we're going to be talking about this half of the butterfly, which is all about adapting and evolving. And in list form, remember, it looks like this. So under life's principles, that half talks about life adapts and evolves. And there's 3 main strategies, as you recall from the butterfly here. We've got these 3 main strategies. They're kind of greenish in the butterfly. One is that life is locally attuned and responsive. Another is that life runs on cyclic processes or integrates cyclic processes. And then the third is that life is resilient. All right, so why do we need to adapt and evolve? Why is that part of life's principles? Well, again, we get back to the Earth's operating conditions. Now, we've got these 3 conditions. The adapting and evolving is really in response to the fact that conditions on Earth are in a state of dynamic non-equilibrium. So if conditions are constantly changing and it's not predictable, what you need to do in order to accommodate that is to be able to constantly be able to adapt, which is a shorter term thing, and evolve, which is a longer term thing. So we have as you've read, or you will be reading about life's principles, adapting and evolving happen at all different scales, from instantaneous to very, very long term. And then the other reason why it's important to be able to adapt and evolve is that Earth is full of limits and boundaries. Limits might be the limit of like the edge of land, and boundaries, same thing. Limits could be the amount of sunshine hitting the Earth. It could be the amount of food that's available within a given location. So these are the operating conditions that we're really targeting and focusing on when we're trying to stay alive, meet all those conditions of being alive, and within Earth's operating conditions. Okay, again, this will help you, it helps me at least, to see the context. So refer back to the butterflies. You can kind of see where these fit in and why they help adapt and evolve and why they help meet Earth's operating conditions. Okay, so this first one is that life is locally attuned and responsive. So we know that life adapts and evolves, and this is a fundamental principle, as we said, because the conditions on Earth are always changing in the dynamic non-equilibrium. So organisms individually and collectively must be able to adapt and evolve in order to survive. So how do organisms adapt and evolve? Okay, so the first of the 3 strategies is that they have to be locally attuned and responsive. This means that an organism has to be constantly sending out information, receiving information about the world around them, whether it's sound, heat, movement, pheromones, and then an organism has to respond to this information appropriately. This is called a feedback loop. So you have to have the antenna, you've got to be able to send it, right? You have the signal, that's what information is being shared, and then the key is you have to receive the information and be able to respond to it. So we have to have all 3 components at the same time, and that response has to be appropriate. So for example, this little frog is sending out its signal. It's got a visual signal here, right, with its throat. It's got, as we know, a sound signal. It's also sending out signals with its colors, but in that particular case, it's sending out a sound signal that other frogs hear and respond to in an appropriate way. It might be a mating call, it might be a sign of distress or warning that a predator is coming. Other frogs of that species will respond appropriately to that. Interestingly, other organisms in that little ecosystem will hear it and also know what that means, and they will too respond appropriately. So you have to have all 3 of those things. Another type of antenna signal response is you'll see in a chameleon. So it responds immediately to its surroundings by changing color. So the antenna doesn't have to be a literal antenna, it's a sensor, right? It's a way to send information, a way to receive information. And that information is what we're calling the signal. Okay, another way to have a feedback loop is to learn and imitate. So it's interesting, we always think of ourselves, humans as being smart and figuring things out, but other things in nature do the same thing. One of which we see here is this gorilla. These gorillas move territory when they're running out of food in a given area. They move on, but when they get to a new territory, it's unfamiliar. There's a lot of unknowns, and there could be a lot of hazards. So what they do is they send out the young teenage males who are the most adventuresome and the most risk-taking to go out and try out new plants, and then they watch to see what happens to them. Now they're not only the most adventuresome, but they're also the hardiest, right? So they're full grown almost, but they're really young and healthy. So they go out, and then the rest of the group watches what happens. And if they don't get sick or they really like it, then the rest learn and imitate that behavior. Sort of an interesting reverse version of that is these Japanese macaques. So apparently they live on these islands and with all these geothermal pools, so these hot pots, natural hot pots. And apparently people would go there on vacation and just enjoy sitting in these hot pots. Well, the macaques watched this and they started doing the same thing. So it's sort of reverse biomimicry, or actually it is biomimicry because humans are natural, right? So other organisms practice the same thing. They learn and imitate. And so now they spend a lot of time in there and just run out to get food. So I think that's pretty interesting. So another type of antenna signal response is you see here with these ants. So what ants do when they're in their little ant colony, they'll go out and look for food. And if they find it, as they head out of their ant colony, they leave one kind of chemical trail, which is that tells other ants, I'm on my way out. If they find food, then they leave a different sort of trail on the way back. And so when the next ant goes out, it senses the trail and says, oh, this trail is hot. I'm going to go to the very same place to find food. Now, if that food runs out, or if the ant comes back without finding food, it leaves a different sort of a trail. So the ant knows, oh, don't go there because I know there is no food in that direction. So that's how they can communicate with each other, and there'll be a diminishing return after a while. So as the food runs out, there'll be fewer and fewer ants taking that path. So again, that's an example of a feedback loop and how they can be locally attuned and responsive. The key here is really that the information is appropriate for the intended receiver, and that the receiver is able to receive it and then able to do something appropriate with it and then continue that feedback loop. So the idea that life runs on information. So that's something we can be thinking about when we're doing sustainable design, using information instead of materials, setting up all three components of the feedback loop, and how can our designs learn and imitate. So the second strategy on that side of the butterfly for adapting and evolving is to be locally resourceful and opportunistic. Nature's resources are locally limited, right? Successful organisms make the most of what's locally available, especially things that are free and abundant. Strategies for being locally resourceful and opportunistic include using free energy, using shape rather than extra materials to meet needs and particular structural requirements, and also using simple common building blocks. Now, free energy includes sunshine, that's what we think of the most, but it also includes wind. We know a lot of plants rely on wind to do its distribution of seeds and pollen. It also includes rain. So these lily pads, stay clean because rainwater is able to wash them off, and they have a special surface texture that allows them to be rinsed clean with just rainwater. Gravity is also an example of of free energy. So we take advantage of that all the time without even thinking of it, right? So it's an excellent form of free energy. Using shape rather than material to perform needed functions is cheaper and more resourceful. So again, we're getting back to those functions. One that you can see, many of us live in a place where there's maple leaves, and other leaves do this too. When there's a really strong wind, you'd think that the leaves would get shredded and then pulled right off the tree, and some of course do. But one strategy they use, they're shaped in such a way that when wind blows over them, they curl up and they form this this sort of tube, and they kind of spiral a bit so the wind is able to blow off them. So they bend in the direction of the wind and then form this nice little rolled up spiral tube to avoid getting shredded or pulled off. Another one, it's one of my favorites, is a spiral you see in nature. This is a cutaway of a nautilus. So this shape performs all sorts of functions for the nautilus. We talked about, I think we've mentioned this before, it allows for infinite proportional growth. So each of these chambers is exactly the same proportion as the one before, and of course that can go on infinitely. It provides this, allows it to function fully as it's growing. So every stage it has the right proportion so it can do what it needs to do. So you see that using a shape rather than material to perform a function all the time in nature. All right, another one is using simple common building blocks. We talked earlier about DNA and how all of us, you, me, and this maple leaf, this dung beetle, we're all made from essentially the same DNA. We have very little variation. The number of base pairs and then the order, of course, is what differentiates us, but we're all made of the same 4 base pairs. This means we can share information, and it ties into other life's principles too. And we use the same common building blocks. We talked about that too. Carbon, hydrogen, oxygen, and nitrogen, and then a few others more form virtually all of life. So we have these simple common building blocks using different sorts of information allow us to perform virtually every function that we want. Being resourceful and opportunistic can be really obvious. Like this dung beetle uses what's locally available, free and abundant. In this case, it's dung, and they use that. They stick their eggs in there and they roll it up, and makes this nice little package for reproduction. So that's what we mean by locally attuned and responsive, and the resourceful and opportunistic part. Okay, so the next one, life integrates cyclic processes. Recycling also happens on the other side of the butterfly. It's important to understand, again, why recycling or having cyclic processes is so important. And this feeds into because life needs to adapt and evolve, and it's because there are changing conditions on Earth. And I'm going to keep emphasizing that because it's really easy in the world of sustainability for people to take one concept and run away with it. And if they get the concept, they get the words right, but they get the purpose wrong, and they do more harm than good. Drives us all nuts, doesn't it? So when you're looking at life's principles, you always have to relentlessly ask yourself, why? Why is this strategy important? Why is this function important? Why is this principle important? And why does it help things survive on Earth, giving Earth's operating conditions? Okay, so I'm going to keep hammering on you about that. So this strategy for adapting and evolving is to run, that life runs on cycles or integrates cyclic processes. Earth itself, of course, is turning around, so it runs on a cyclic process, night and day. So it's spinning on its own axis, and it's revolving around the sun. So we have seasons. So these are the primary cycles of Earth, and so organisms have to follow those daily and seasonal cycles, right? So that's what we're seeing here. As you know, many of life's processes are also cyclic. We've got birth, life, and death, right? So we've got this longer term cyclic processes. We also have inside our bodies. Remember we talked about your own body being a great example of strategies and systems, or our human circulatory system is an excellent example of a cyclic process. The fact that we have blood running around our body really rapidly, I forget how quickly blood circulates through the body, but it's so quick that if you, for example, step into the street and all of a sudden a car comes in, turns a corner and right in front of you, it's going to hit you. Your adrenaline is excreted into your system and runs throughout your body almost immediately. So you get that panic and you jump back, right? So we couldn't respond quickly. We couldn't adapt and respond quickly if we didn't have that constant cycling around our body. And you can imagine all kinds of other scales and examples of why having circular systems is so important to be able to adapt and evolve. Your skin's another example. When you're on the sun, it'll turn darker. So then, the more sun you get, the more it protects you against sun, right? Of course, that can go too far. And if you use your hands a lot, for example, I took up rowing recently, and you get these crazy calluses on your hands. So your skin, because it's constantly cycling, right? You've got these layers of skin, you're constantly losing the external layers, and you're generating new from below, allows your skin to adapt quickly, like us responding to the sun, or say when you're cold and you get goosebumps, or longer term, like getting calluses. So the ability to adapt is also dependent on cycles. So we talked about our fight or flight requires constant and rapid circulation and appropriate hormones. And also we need to be in constant motion. So doing a process over and over again allows us a chance to correct each time. And in fact, this comes into play, as you'll learn next week and beyond, with the spiral process, why the spiral is so important. We'll talk about that again. The fact that you go through a cycle each time gives you a new opportunity to learn. So trial and error doesn't work without repeating cycles. So if you make a mistake and you can't get a chance to learn from it, that doesn't really help, right? So trial and error works really well when you have repeating cycles. So that's some of the reasons why feedback loops are so important, okay? It's a cyclic process. Okay, so life's third strategy for adapting and evolving is to be resilient. And before we go into this, I want to really be clear on what resilient means. You hear that term all the time now. People are picking up on this, right? And it really is coming from biomimicry, but or at least coming from nature. But we have to understand what that term means because people use it inappropriately. It drives me nuts. So being resilient is the ability to come back, recover after a disturbance. Okay, that's different than being robust. That term is used in engineering also. Robust is being able to operate the same way under all kinds of different conditions. That's also important, but that's not a principle because not all creatures need to be able to survive many different conditions. But everybody has to be resilient, so able to recover after a disturbance to itself, to its system, to its species. Okay? So that's really important for you to understand. Now there's 3 strategies life uses to be resilient. One is redundancy, another is to be decentralized and distributed, and the third is diversity. So by redundant, again, this is a term that people sort of get confused with, but redundant means achieving the same function in more than one different way. Okay, so if you want to, so for example, Boeing has learned about biomimicry, but I think they did this before they learned about biomimicry, that systems in the airplane that are really important, they have 2 or 3 parallel systems, so it's repeated, right? But the difference between repeated and redundant is repeated means it would be the same system 3 times, 2 different backups. But redundant means they have 3 different systems. One might be electrical, one might be pneumatic, and one might be hydraulic, for example. So if something with electricity fails, they have a completely different system that won't fail under that kind of disturbance. All right, so that's what redundant means. And an example of that is when we look outside, we see green all over the place, right? We see it at different levels. We're seeing kind of one massive level here, but it's up higher and down lower. If you go outside, if you run outside right now, and if you don't live in an urban area, but a little bit suburban or natural area, if you run outside and I said grab a leaf, you could probably grab 10 different kinds of leaves, right? And different shapes too. It could be in needles or blades of grass or big leaves, or it could be in lichen, or it could be in algae. all of that is photosynthesizing. So photosynthesis is so important to living things that there's a ton of redundancy built in. So you have all different kinds of ways of photosynthesizing in all different shapes and forms. So if one part goes down, there's plenty others to take its place and fill in. This also is a good example of decentralized. You don't see one big leaf out there or one tree or one plant doing all the photosynthesis. It's everywhere. So if something is important, you want decentralized, so one hit won't take it all down, and distributed throughout a system. All right. And redundancy too. You've got all kinds of different ladybugs here, for example, right? So we've got all of them appear to be the same, but they're all slightly different, right? So if something happens, there'll always be something in there that'll make the species survive. Diversity. Again, there's diversity within here. We can't really tell, by looking at this little tiny picture. But a big obvious example is when we have mutations. So these are both tigers. This one's albino. Most of the time, this diversity won't matter at all. It's not going to affect this guy one way or another. But in a case when you're trying to blend into brownish grass, this guy's going to be in trouble, right? But if there was suddenly a cold period and there was snow, well, these guys would be seen, right, by their predators, and these guys wouldn't. So having diversity means that if there's a change in your system, somebody is going to survive and be able to carry on. Now, to do that, we have to be able to cross-pollinate, right? We have to have pollination, and we have to have mutation. And the reason we can do that, as we've gotten back to before, is that we've got shared genetics, and that gets again back to the simple common building blocks. And as you'll see when you explore life's principles, there's a lot of crossover. That's why I try to use some of the same graphics repeatedly, so you get the sense that there's that they're all sort of interconnected, interdependent, which is one of life's principles we'll talk about next. Okay. All right. So that's it for adapting and evolving, and next we're going to be talking about how life creates conditions conducive to life.